Welcome back. So last time what did we do last time? We started out with Maxwell's equations in differential form. We talked a little bit about what these guys mean physically. Importantly, we are getting a handle on all the field quantities of electromagnetics. So when we go down, we start to solve these equations in different ways. We'll have everything at our fingertips. So for example, we have D and E, which are the electric fields. We have B and H, which are the magnetic fields. And they are all responsive to charge and to moving charge. These equations, as I talked about last time, can be viewed as four first-order, partial, differential equations that are forced and are coupled. And they're coupled if things change as a function of time. And in this course, that's the fun of it all. Things will change as a function of time. We are going to play with these equations so that we understand what they mean better, and we understand what the terms in them mean more. For example, one of the things we did last time was we played with this equation here, del dot D equals rho. We followed a prescription that we're going to follow all along, which is to take a derivative of both sides. In this case, we took the time derivative, we did some mathematics, and we inserted, for the del D del T term, we inserted another one of Maxwell's equations. And with the dust cleared, we got the continuity equation, which relates the time derivative of charge to moving charge, which is current. Okay. So where does current come from? It comes from moving charge, or a change with respect to time of a charge density. Very intuitive concept. And from a physics perspective, a conservation law. Charge is neither created nor destroyed, it just moves around. Okay? So we call this the continuity equation, and the conservation law is embedded perfectly in Maxwell's equations. So it's not really a new independent equation. We can't really use it separately from Maxwell's equation, but it's part of the information that's embedded or stored or hidden even in Maxwell's equations. And if you take a look at that, you'd be pretty hard-pressed to point to those terms and say, there's the continuity equation. So we had to use the mathematics of vector algebra to be able to unearth a new physical fact. Okay? So we just took it for granted that it was fun and easy to mess around with it mathematically, and after doing that, we came up with new physics, or a new understanding of what these equations were. And we're going to repeat that again and again and again through this course. By kicking these equations a little bit, by messing around with them mathematically, what we're going to do is we're going to tease out of the equations, more and more and more interesting facts, which will lead to better decision making, better understanding. Boundary conditions, because we're solving the differential equations subject to boundary conditions. You know, you solve a differential equation in time subject to an initial condition. Well, these are differential equations in space, so we call the limits of them or the edges of them boundary conditions. So what happens to the fields when I move from air to glass or air to metal? Okay. We have material properties. We have material properties where now I was very sloppy, and I think someone called me out on that last time about the difference between D and E and the difference between B and H and all. And when we were getting our feet wet, when we were just warming up to the subject, I trivialized and said, hey, D and E are just the electric fields, B and H are the magnetic fields. Well, there is a distinction between the two. And these are the equations that give rise to that distinction. So everything about free space is written here and here. Everything about the materials are embedded in a potentially complicated polarization vector and magnetization vector. So two new equations, two new unknowns, we've said absolutely nothing. but we have provided a structure for looking at a lot of different materials. Okay? Materials, by the way, are the only way that Maxwell's equations become hard. Okay? If the materials are simple, if they don't change as a function of time, if they're or change as a function of position, or if they're linear, then Maxwell's equations are coupled, partial, first order, forced differential equations that are linear in time and shift invariant. And if you're in a signals and systems class and you say linear time invariant, LTI, then you jump up and down and you say Fourier. Okay? So for simple materials, Fourier analysis works wonderfully on these equations. Okay? And we'll do that. If for simple materials, the relationship between D and E and the relationship between B and H was just a constant term. Epsilon and mu. Epsilon has units of farads per meter. Mu has units of henries per meter. And so a farad reminds us of a farad, not a ferret. A farad reminds us of a capacitor. And a henry reminds us of an inductor. And so there is, in fact, a capacitance associated with free space, and a capacitance associated and an inductance associated with free space. We still have to scratch our heads and figure out what exactly that means, but it does again remind us that there's a lot to be learned in the context of Maxwell's equations from circuit theory, inductors and capacitors, LCs, RCs, LR circuits. And what's interesting about that, and is, well, it should be that way because Maxwell's equations, when the time derivatives go away, become circuit theory. In other words, the loop, this curl of E, if there's no change in B term, that's Kirchhoff's voltage law. This equation here is Kirchhoff's voltage law, the sum of the voltages around a loop, which would be 0 if there was no time dependence in our problem. And if there is a time dependence in our problem, then that loop captures whatever change of magnetic field there is, either as noise or as a signal in a little loop antenna that sits on the back of an old black and white television set in your bedroom when you were a teenager. Well, if I have a capacitor and if I have an inductance, then I should also be able to account for loss. And so I add Ohm's law, V equals IR, to the mix, where I also have a third material property, which is how hungry that material is for electromagnetic signals. And if I have a sigma in there, if I have a finite conductivity in my problem, then it will take the field away from the electromagnetics of the situation. It will take that information and it will move it out of the problem itself. So it is a dissipative term. More frankly, it's a loss term. Okay? So I have LC and now I have an LRC. That's all we are. That's there's going to be some other ways of thinking about materials, but at some level, it's as simple as that. The materials in an electromagnetics problem are going to look like capacitances, inductances, and resistances, and maybe what that means is we have to understand what those mean better, right? But you've had a lot of experience with that, and we can use that. Oh, I'm sorry, there was one more equation I was talking about, which was another interpretation of E and B, another manifestation, another physical manifestation of E and B, that I know you studied, and probably as a high school student. And that is the electric field will give rise to a force on a test charge or a little electron. And a magnetic field will do the same as long as that electron's moving. And by the way, if I have both an E and a B, then the E will start the electron moving, and then the B will start to spin it around. Right? So the electric field acts to pull or push the charge aligned up with its vectors. And because of this cross product, the motion of the electron the force will be perpendicular to the velocity and the B field. So I don't know if you were like me, you took your right hand and you walked around VBF, VBF, VBF when you were doing mass spectrometer problems or things or problems like that in your probably your high school physics class or certainly your freshman physics class. So in my goal of introducing all the quantities and trying to get to know all the quantities of electromagnetics, well, the force is a very important one as well. And so a physical force on an electron or a proton or an ion is governed by an equation that's very, very familiar to you, and we shouldn't lose sight of it. It is fair game to play with and solve whatever problem you face 5 years from now in electromagnetics. Okay? I want to do something else today, and it's going to introduce another vector quantity, and it's going to take the form of playing around. Again, when I get bored, I just do math. I'm sure you guys are the same way. And I'm going to take a couple of Maxwell's equations, and I'm just going to play with them mathematically and see what happens. Okay? And by the way, this derivation that I'm going to do for you today is a very, very useful derivation because there's not going to be a lot of approximations. I don't have to specify coordinate systems. I don't have to specify too much of my material properties. And for that reason, the derivation that we're going to have is going to be very, very, very powerful, both intuitively, so that you can make intuitive, inventive decisions, intuitive inventions and intuitive decisions. But it's also going to be numerically and computationally important for a wide, wide range of problems because it is so darn general. Okay? So it's a very, very, very useful theorem, and I might as well name it. And if you want to look back at these notes later on, you'll find the heading under the Poynting theorem. I think Slater and Frank does a really good job of this theorem. And what I'm going to do again is just sort of play around, probe, bug Maxwell's equations. And the ones I'm going to start with are my favorites. Whenever I ask the students for 10 years of teaching this course, every time I ask what your favorite equation is, somebody in the audience is going to say divergence of B is equal to 0, which is fine. But when you after a while, you just get so bored of that stupid scalar equation. These curl equations they're so much richer and so much more interesting. I know they're more sophisticated. I think it's probably the difference between, PBR and a good craft beer, right? I'm sorry, that's probably off color. I'm going to get in such. I'm becoming much more flippant with my tongue. I'm going to get in trouble here pretty soon. I'm going to get even more trouble if I don't remember that that's a del D del T instead of a del B del T. Okay, so those are the two curl equations. And those have a lot of information in them. And so for that reason, I'm going to kick them around. And what I want to do, this equation I view as primarily for the H, and this equation I view as primarily for the E. So this is and it's not fair to say it that way, but it's useful in any way. And so what I want to do is I want to take the H part of this equation, and I want to blend it into the E equation. and I want to take the E part of this and I want to blend it into the H equation. So I want to mix the information together in a way. And the way I'm going to do that is I'm going to multiply the top one by H, and I'm going to multiply the bottom one by E. And because I'm dealing with vectors, I have to pick how I'm going to mix them, or how I'm going to multiply them. Same word. And so I'll do the dot product. And so those of you who like the scalar nature of the del B, the versions of B terms, I'm coming there. It's okay. We'll get there. We'll get away from that. And then the E dotted with this guy here. So now when I multiply the top one by a magnetic field, I'm taking the magnetic information and I'm putting it in the top equation. And when I multiply the bottom one by the electric field, I'm putting that information I'm mixing that information. So now what I'll do is I'll add the two together, or I'll take a superposition of them together, and I'll subtract them. Adding is subtracting. They're both a superposition of the other. So I'll bring those down together. And what I get is a little complicated for a little while. My left-hand side has those two terms in them. My right-hand side is actually kind of nice, or almost nice looking. Did I fit that all on the screen? Okay? Yeah. So the left-hand side is a little cryptic still. The right-hand side is sort of a mixture of H and B, a mixture of E and D, and a mixture of E and J. Okay? Okay. Now there's a vector identity. There's a vector identity here. And a vector A dotted with the curl of B, B dotted with the curl of A, minus sign together, is the divergence of E crossed with H. Okay? So the left-hand side here can be written as a vector identity. And what I'd encourage you to do is to leave a page or two in your notebook and work that out in Cartesian coordinates. Okay? It's not that simple, but I mean it's not only 2 lines, it's probably a dozen lines. But if you do that, at least you'll prove that vector identity. And it's worth doing just to get comfortable with it. Okay, it's kind of like the chain rule, it's kind of like not the chain rule. It's kind of like the multiplication distribution, right? It's like a distribution. So I've got A times B times C minus B times C, and so I can rearrange those guys. The minus sign undistributes. It's a distributive rule, but it's applied to a vector, a triplet, where one of those vectors is a del operator. Okay? So take a look at it, you'll get more comfortable with it. And to really breed familiarity, work it out in Cartesian coordinates and you'll be real happy with it. And if you're happy with it, you'll remember it better and use it. And if you use it, you'll do things that other people can't. Okay? So that's your left-hand side. Now, let's take a look at that a little bit more carefully. We can learn a lot just by trivially playing with units. The units of E are what? Volts per meter. The units of H are? And the units of the del operator? 1 over meter. So the denominator here is per meter cubed. The denominator here is per meter cubed. So when I think about a per meter cubed, I think about like a cubic centimeter or a cubic meter. So I have a volume, right? So this on the left-hand side, there's something per unit volume, per length times width times height. Okay, and that something is a volts times an amp, which is watts. Watts, right? So the watts are power, right? Energy per second, power. So the amount of watts stored in a cubic meter is what's going on in here. Okay, just from the units, there's something valuable about watts, meters. If I want to know the total amount of watts, then I should add up the total number of, I should integrate across the total number of meters that I have. So a dV integral will give me watts back. And then if I don't like watts and I want energy because I want to heat up I want to charge my battery, or I want to heat up a glass of water, then I should integrate over time. Okay. So what we're talking about with this manipulation is we are right at this point. We're talking about power, energy, those kinds of relationships, and that's going to be very, very useful if I want to know how big a power amplifier I need to buy for a radio station that wants to serve not only Dallas, but also Dallas and Fort Worth. Right? So answering link budgets, answering questions like, if I have a spaceship that's circling Mars, how much power can I receive from an antenna and a battery and a transceiver that I've managed to place on that spaceship around Mars, and therefore how many frames do I need to average before I actually get a picture back from that spaceship? Okay, so all these kinds of link questions, all these kinds of high level, will it work kind of questions, is what the role or what the purpose of this mathematics are. Okay, so that's the left-hand side. Oh, the other thing I want to remind you of is we're starting with the divergence theorem, and with some of the other utilities and some of the other times that we've used divergence. We're starting to get an intuition that a divergence, and by its very name, a flux of things. So whatever this quantity E cross H is, which has something to do with powers per meter squared, this divergence of that is the flux of that power. The flux of that power per area. Okay? So there's a clue there from the divergence in front of that. So not just the units, but also the symbol del dot. Okay. All right. Now let's work on the left-hand side. And for the left-hand side, what I'm going to do is, okay, so I've got an H and a B, and I've got an E and a D, and I've got an E and a J. And I'm sorry, but I've got E and H on one side, and I've got a B on this side. So I'd really like to change that B to an H. And I'd really like to change the D to an E. Okay? And I know how to do that now. I know how to do that now because I took some time and I talked about materials. So I'm going to be, for now, eventually I'm going to get down to these kinds of relationships. But because this is so general, I want to keep it general for a little bit. I'm going to keep the polarization and the magnetization in there. Okay? I'm going to include this P and include this M. And when I do that, remember, I can cover a multiplicity of sins of the material. I can cover whatever that material wants to throw at me in terms of complexity. I can cover that as long as I have a way of calculating P and M. I can never miss a chance for a digression. Maybe I should have done this last time. P and M have to come from somewhere. And if you're in a perfect world with perfect information, with perfect theoretician skills, theoretical skills, where you would do is you would go into some kind of a material science to find out how to calculate the polarization and the magnetization. And dollars for donuts, what that means is you're going to do quantum mechanics. So what you're going to do to find a polarization for a particular system, for a particular material, is you're going to do the quantum mechanics of one molecule or one atom of that material. Okay? So you're going to look at that molecule, that atom of the material. You're going to apply the rules of quantum mechanics to it. That'll tell you what's happening on one of those little elements. But this material is macroscopic, as is Maxwell's equations is macroscopic. And so what I have to do is I have to very carefully add up the quantum mechanical response of each and every one of these elements, each and every one of these atoms or molecules, into a whole. And that's called statistical mechanics. Okay? So in this course you're taking electromagnetics, or fields and waves. To really understand these equations, you've got to take 2 more courses. Quantum physical electronics, which will cover what a single electron's doing. And then something that we don't really stress very much, but statistical mechanics. The careful adding up of an ensemble or a large number of these. And then when you do that, what you're going to find is, wait a minute, you need the electromagnetics of these equations, for example, the potential, the voltage, or the electric field, or the forces, before you do the quantum mechanics. And you need the quantum mechanics and statistical mechanics before you do the forces. So it's not just one course, another course, another course. You're going to have to circle back around through this loop again and again and again until you get convergence. And so that is the problem-solving methodology, or that's the dogma, if you want, of how you do the theoretical part of materials into Maxwell's equations. Okay. So that's kind of what's going on there. If you get a chance, I really recommend you take this quantum physical electronics course by Bill Frensley. He's absolutely brilliant, and it's absolutely a unique and special course that we offer here. And it's head and shoulders different and above what you'll find at other universities. So I would recommend, just for fun, elucidation, and utility, to take that course from that particular very, very special professor, Bill Frensley. Okay. He doesn't pay me anything for that announcement. All right, that was my digression. That's just a little bit of a break from the mathematics. So what I want to do for this B field here is I want to substitute in mu naught H plus M. Couldn't be simpler. And what I want to do for this D field here is substitute epsilon naught E plus P. Again, that couldn't be simpler. How many vectors did I not label? There we go.
So why don't we use the other one where it's just epsilon naught, epsilon r times E for the electric field? Why is this one?
Hang on. I knew I had a mistake in here. Sorry about that. Okay. I will do that eventually.
But they're the same though, right?
No.
Oh,
No. That's excellent question. Excellent question. The question was, why didn't I just go ahead and use these forms and plug those in? This is very general. Okay? So this contains, so P can be nonlinear. P can be changing as a function of space. These P's and these M's are, don't let them fool you, they are complicated. Okay? Now, for many materials, we don't need to worry about the complexities. Okay? For a block of glass, for example, it's very rare, although it happens, that a block of glass is nonlinear. Only in very extreme situations, like if you're going 6 megameters from coast to coast on an optical signal where you've confined your electric fields to 9 micron diameters and you've kept it at that radius for 6 megameters, 6,000 kilometers, are you going to see the impact significantly of nonlinearity in a glass? But if I'm just looking through a screen, it's just a silly block of glass. So in the many instances where our materials are incredibly simple, then I can just describe them as a simple constant. Okay? So I don't want to quite pull the trigger on that yet. Okay? And I will soon enough, don't worry. But for now, I want you to have an equation that has the full complexity of the material, even if it's buried into just a couple of time derivatives. Okay? Notice I did use the simple expression for the dissipation. Okay? Notice that I have a mu naught here and an epsilon naught here. Let's do a quick sketch, a bad sketch of the units here. I have a volts from the electric field here. I have a volts from the electric field here. So I'm going to have a volt squared. And the conductivity, remember, is units of mhos, which are 1 over ohms. So that last term is a v squared over r term. So if this indeed is power, this is how power leaves the electromagnetics of the situation. If this is power, then this is how the power leaves the electromagnetics of the situation. And let me give you a simple example of that. Have you ever possibly used these newfangled things called microwave ovens? How many people have actually used a microwave oven? You've never used a microwave oven.
I don't use it.
I don't like it either, but have you ever?
Yes.
You have, so you should raise your hand. I don't use it either. I don't like it, but they scare the dickens out of me. No, that's not why I don't like it. But imagine, so take a styrofoam cup, put it inside the microwave oven, and hit high and hit 20 minutes or 10 seconds or whatever it takes. And a magic miracle thing happens when the buzzer beeps and opens up. You take out the styrofoam cup of water, and now it's scalding hot. Okay? What has happened is the energy of the electromagnetics that's in the cavity, in the standing wave cavity of the microwave oven, has left the electric field and left the magnetic field and dumped into boring, plain old heat. Okay? And so that flow of power from that microwave oven experiment, which I know you're dying to go home and try now, you're going to dust it off and do this experiment because you don't believe me. Because it's been so long since you've used it, you're looking at me incredulously. But try it. That's what's going on with these mathematical terms. When I say heat, when I say dissipation, when I say energy is lost, what I'm saying is it goes into a frickin' thing of a styrofoam cup of water, and it heats up. I can make toast with electromagnetic energy through this term. Okay? And it's really, really, really hard to take that hot water, pour it back into the microwave, and turn it back into electromagnetic energy. It just doesn't happen that way. Right? I've got to set up a turbine, I've got to spin some wheels, I've got to charge the battery, and then I've got to put it back in, and it's very, 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 very lossy. So this is downhill. This is where entropy comes from. This is where thermodynamics comes from. We leave electromagnetics and go into heat transfer and thermodynamics through this term. Okay? That's what I'm trying to get at here. You can also think of it as a circuit element that is a resistor. Right? and therefore still part of electrical engineering. But even on that case, it's a loss. Okay? All right, enough on that.
What happened to that meter square?
What happened to what?
The meter square, for the electric, the volts per meter, right?
Oh, yeah. I see that little squiggly line? That means I'm lying to you. That means that I'm being sloppy. And so what you're going to do in your notes is you're going to fill in the details and double check me on that. Okay? But the analogy is more important than the meters. And that is a V squared over R, which I think you should recognize and that's the physical interpretation of that term. Okay? All right. The right-hand side I'm going to change again. Oh, sorry. So I'm going to take these two terms here, and it's really impossible to think about going from here to here, but if you think about going from here to here, it's fairly straightforward. The first thing you do is you notice that the mu naught of free space and the epsilon naught of free space is a constant. I'm sure there's a few theoretical physicists that will want to start a fist fight over that, but as far as I'm concerned, the dielectric constant is a constant. The permeability constant is a constant. And so I can pull that through the time derivative. Okay? Even if it changes with space a little bit, it's still not going to change with time, so I'll pull that over. And then I have an h del t. But take a look at what this guy is. This is a del h squared del t, and if I take the derivative of that, I get 2h del t, which is exactly what I have here. So if I can go backwards easier than I go forwards, but it's still an equality. An equality is an equality. And so now I've written this funny looking derivative as something that goes as amps squared and something that goes as volts squared. Okay? And then I've got a couple of other terms here. Now take a look at this guy here. I have a 1/2 in there. I have henries, so I have an inductor there. And I have amps squared. This guy here is a 1/2 Li squared term. And look at this guy here. This is my volts squared. And this is my farads. So I've got a capacitance and I've got a volts. So that term looks like a 1/2 CV squared term. So the energy stored in the capacitance of free space and the energy stored in the inductance of free space are found here and here. So I've got an LRC construction here. But it's very, very, very general. It's not restricted to circuit theory. Okay? If I go ahead and put a material, this is free space, this is free space, this is the draining from the system into my styrofoam cup of water or my toast in the toaster. These two terms are now materials. And so additional energy can be stored in the magnetics of the material, and additional energy can be stored in the polarization of the material, the electrics of the material. Okay? So that's the role of the magnetization and the polarization. In case you were wondering, when I introduced it, The role of this polarization and magnetization is inherently to provide the material response, and in this particular case, to provide the energy associated with the material. Okay? So if I've got atoms that are vibrating in a crystal, the vibration is an energy term. And the energy that's stored in that vibration as it pertains to the electromagnetics is going to be found right here. If I have a magnet and I line up all the magnetic domains in it, the organization of all the magnetic domains so that I have a north pole and a south pole, so my iron nail turns into a bar magnet, then that order becomes a type of energy that falls into this magnetization term. Okay? So that's what this derivation is starting to tell us. It's starting to understand, it's starting to describe the Poynting theorem, is starting to describe the energy-power relationships of the electromagnetic system. And it's doing so in an incredibly general manner. Okay? In this one equation, I'm talking about microwave ovens, I'm talking about toast, I'm talking about bar magnets, I'm talking about LRC circuits. If I ask the question, if you think about this, and you say, well, wait a minute, how can free space by itself store electromagnetic energy? I mean, that's a valid question, right? And so let me use this example of this room here. There's a lot of free space between us, right? This room is mostly empty. It's mostly free space. You've got desks. You've got people in it. Right? You've got rugs on the floor. Not much else. You have light sources in the ceiling. These fluorescent light tubes. And the emission from that are electric waves and magnetic waves. E and H. And when it hits our eyes record the energy of the light that happens to hit the retina of our eyes. Okay? Now think about it. Light moves about a foot a nanosecond, right? The speed of light is 3 times 10 to the 8 meters per second. We all remember that? I always remember it as well, as light moves about this far in a nanosecond. A foot a nanosecond, a gigahertz. Okay? And so if you trace out the number of feet from the light to your notebook and back into your retina, it's probably 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nanoseconds, 10 feet. So if I can freeze time in the 10 nanoseconds that light is going from the plasma tubes to the desk and then back up to your eye, that energy has to be somewhere. That light energy has to be somewhere for the 10 nanoseconds that it takes to travel from the light bulb into your eye. And that's what these free space terms are doing. That's what these free space terms are doing. Okay? That's how energy can be stored in simple free space. One example of how energy can be stored in fields in free space. That microwave oven, right? There's energy outside the styrofoam cup in the cavity of the microwave oven, right? And that energy that's stored and bouncing around off the walls of the magnetic of it are these two terms. Okay. All right. We now now what we'll do is we'll make these very simple. We'll do exactly what you recommended. And we'll dumb down the problem and say M and P are just simple, trivial responses to the electric field, to the magnetic field and the electric field, respectively. To be specific, I'm going to use these formulas here. The polarization is epsilon naught times the susceptibility times E. Magnetization is mu naught times the susceptibility times M. Units of the susceptibilities are dimensionless. Just as a reminder, this is a review. Anybody see any glaring mistakes? I think I got it okay. Oh, can you not read it? There. Yell it.
But the A shown on top is missing.
Oh, this little guy here? That's not a mistake, that's just a typo. But you're right. I'm always good for something like that. And then I can rearrange these guys, I can collect these guys. I'm offering this more as a review than anything else. You can now see what happens when I add the material, a simple material, into free space. In other words, in certain situations, what I can do is I can flood this room with a material, and I can store more energy on the transit from the light to the table and back up to your eye. If I flooded this whole thing with water, there would be an enhancement in the energy storage capability because of that water. And so for the moments before you drowned, there would be more energy stored in the space of the room. Well, even after you drowned, I suppose, but you can't really show that. Well, never mind. But and you see the mathematics brings that out perfectly, right? You're just adding in an additional material response, and in this case, it's a very simple material response. Okay. And next time or the time after, we're going to go into a litany of all the ways that materials can be hard. And interestingly, you'll actually learn how to handle those within that same context. So it's kind of a nice thing. All right. What I'm going to do. I'm going to abstract this math a little bit so that we become explicit about what we've been talking about. This term, all this junk here, the h squared and the 1/2 L, all this is the magnetic energy density. And this guy here is the electric energy density. So I'm going to define UM and UE accordingly, a little implicitly. And now I can write the divergence of E cross H is equal to the rate of change of the magnetic energy density minus the rate of change of the electric energy density minus the dissipative thermal heating term. Now, when you look at this, you see that this is the divergence of a vector, and that should bring to mind the divergence theorem, right? That should bring to mind the divergence theorem. And if I look at this guy here, I have a density, and that's per volume. And so what I'd like to do is I'd like to integrate through a volume to add up all the energy the change of the energy, not the energy density, but the overall energy in the magnetics and the electrics of the situation. And so what I'll do is I'll integrate both sides by a volume. So we'll integrate both sides over a volume to add up all the energy, to go from an energy density to an energy. The divergence theorem can be applied. So I have E cross H dot n over an area, and that's a closed area, right? So that's the amount of E cross H, watts per meter squared, that crosses that boundary, but I'm integrating across the meter squared, so that's just watts across the boundary. That's just watts across the boundary, and that's balanced by the rate of change of the electric and magnetic energy, and the loss term. So I think it's easy to, I think it's one way to illustrate this is to imagine a very, very, very fast shutter or a very, very, very fast switch where we kill the lights. And remember, the transit times are measured in nanoseconds. That's the relevant transit times that we are sort of used to in this structure. So what we want to do is we want to kill the lights within, let's say, 100 picoseconds or 10 picoseconds. So that the lights go off very, very, very quickly, instantaneously. A delta function turns off the lights. We ask what happens to the light in the room. Well, when it hits the dark carpet, when the light hits the dark carpet, it's absorbed. And the carpet heats up. That's this term here. Okay? It also, some of it finds its way through the cracks of the door and out the windows. And that's just the reduction in the electromagnetic energy in the room. It hasn't left electromagnetics, it's just left the volume of the room. Okay? So that's also the Poynting vectors. That's also this term across those areas. Okay? So that's what's going on in the energy balance of this equation. And this E cross H is so useful and so important that we give it its own name. It's the S vector. It's the Poynting vector. And so that's interpretation, and the fact that it's watts per meter squared, the fact that it's balanced in this energy balance equation, tells us what the interpretation of the Poynting vector is. So if you're doing a link budget from one microwave antenna to another microwave antenna, this is the Poynting, this theorem, this Poynting theorem, this expression is really what you're doing when you're counting up the dBs of the losses of that system. This is the formal mathematical view of what that is. Okay? So one of the consequences of tonight's work is that we have derived a new quantity, a new vector quantity vector field quantity, which is the Poynting vector, which is equal to E cross H, which describes the power flow, the power per area. Okay? And this is what we mean by the Poynting theorem. And again, if you look back over the derivation, you see that it is incredibly general. It is incredibly general. Okay. All right. What do I want to do next? I'm still giving you all the parameters, all the vector fields, right? Can anyone think of one that we haven't touched on yet? Yeah, you're not supposed to know that yet. Or I don't assume you know that yet. I haven't talked about voltage. I haven't talked about the scalar potential. But you're right, there's another two, and probably most of you know this. We haven't talked about the potentials yet. And we know we have to do a little more work because we know we need to talk about at least the voltage field. Right? At least the voltage field. So now we'll work with potentials. This is going to be a reasonably easy derivation, but conceptually there's going to be a really tough step floating by. Okay? And I have to spend a little bit of time talking about setting that one step up. Okay? We know forces and we know energies. Right? So if you have a force, you apply it, push something up a slope, we push something up a slope, we're doing work against gravity, and we've stored energy at the end of that transit. When we do that type of a push, it's F dot dl, right? We're applying a certain force, and we're doing the path integral, the line integral, to get from one position to another position. F dot dl. So we go from forces to energies by doing integrals. If we have energies and we want to know the forces, we take the derivatives, right? So energies and forces are related, but they're related through an integral and then through a derivative. Okay? We see that the electric fields and the magnetic fields live at the force level, right? The electric fields and the magnetic fields lives at the force levels. So what I want to do is I want to introduce purposefully two more fields to live at the energy levels. But I'm not really going to worry so much about units. Who was giving me a hard time about units? Were you? One of you were. You were. I'm not really going to. So instead of using the word energy, I'm going to generalize it to potentials. So there's going to be a relationship, an integration relationship that gets me from the E and the H up to the potentials of electromagnetics. Okay? Now, here's where I need you to listen really carefully. When you do that integration, right? Where is zero? When I'm pushing this up the hill, is zero at the desk, or is zero at sea level? It doesn't really matter. I can call zero the height of the desk. I can call the floor the height of the desk. I can call sea level the height of the zero. What really matters is how far above the starting point I've gone. So if this is at If this is at 0, then I've climbed this up 8 inches. If I'm 3 feet off the ground, then I've gone from 3 feet to 3 feet 8 inches. If I'm 200 feet above sea level, then I've gone from 200 feet to 200 feet 8 inches. It's all the same energy. It all boils down to a constant of integration. When I take the derivative to get back to the force picture, to get back to the electric field issues, whether it's 0, whether it's 200, or whether it's 3, when I take the derivative of that constant of integration, that information goes away. Right? That constant of integration that moves me from force to energy, that constant of integration that moves me from the electric and magnetic fields to the potentials, that's a $20 bill. That's a degree of freedom in my derivation. Okay? That constant of integration is a degree of freedom that won't be that obvious in the course of this derivation. But it's there. Okay? Because I'm moving between a force picture, a field picture, and an energy picture, or rather in our parlance, a potential picture. And there's that constant of integration that when I take the derivative to get back to a measurable quantity, the force on that little electron on a string, it'll go away. So remember that degree of freedom. Remember that I have a degree of freedom. I'm going to take that degree of freedom, I'm going to stick it in my back pocket, and when things look absolutely the bleakest in this derivation, and it will, I'm going to pull that out like magic. It's going to get easy. Okay, and you're going to look at me like, where did that come from? And I'm going to say it's that degree of freedom that's the $20 bill that's buried in my wallet, in my pocket. And I'm pulling it out to spend it on the rainiest, darkest of days. Okay? So please remember that when we work with potentials, we have an adjustment. We can pick an offset. We can pick a complicated offset in that potential, and we can do so carefully and advantageously. Okay? The fancy word for that is called a gauge. But just because we have a word for it doesn't mean you should believe in it. Okay? It's a degree of freedom that's just present. And in fact, it is the degree of freedom that encourages us to develop these new field quantities. Okay? So the reason we're going to develop these, because we have a bunch of tools in our book, in our toolbox. We've got E, we've got H, we've got D, we've got B, we've got J, we've got rho, we've got F, we've got S, we've got M, we've got P. We've got tons of vectors by now. Why do we need 2 more? Well, because of this extra mathematical degree of freedom that will make our life easier. Okay? That's the reason why we're going to go through this thing. All right? Now, what I want to do with these potentials is I want to go back to Maxwell's equations. Okay? And what I want to do is I want to wrap into new fields, a couple of new fields, the voltage, scalar potential being one of them. I want to wrap up into some new fields all the information, not some of the information, but all of the information that's embedded in these 4 Maxwell's equations. So I'm going to introduce 2 quantities, and 2 quantities are going to cover all the information that's in 4 of these equations. So I better do this really carefully. If I'm going to cram all the information that's in these 4 vectors into 2 additional fields, potential fields, I'd better do that process really, really, really carefully. I better use every darn trick at my disposal to be able to shoehorn all of this information into 2 pieces. Okay? And the first thing that I will point out is that we showed, at least in Cartesian coordinates, that there was a vector identity that for any vector A, for any vector A, the divergence of the curl of that A was always, always, always equal to 0. Right? So it doesn't matter what A is, for any vector, this satisfies it. Okay? Well, let's go back to my Maxwell's equations. Let's take a look at that. And if I wasn't so darn flippant with that approximately sign, there's one of your favorite equations, which is the divergence of B is equal to 0. That's a fact of Maxwell's equations. That's a very, very important piece of the four equations. And it turns out that I can satisfy that by setting B is equal to the curl of A. So this defines the magnetic vector potential, the one that you were worried about, now on the table. And what I love about this is I've defined it, I've introduced it, and I've said absolutely nothing. Right? Whatever A happens to be, will satisfy the divergence of B equals 0, because the divergence of any curl is equal to 0. So to some extent I've said nothing, but in another extent I've automatically, without spending any degree of freedom, I've satisfied one of Maxwell's four equations. Perhaps the only thing we've said is that there's absolutely no magnetic monopoles in our system. So who's my physicist that I can't go work for? She's not here. I scared her off. I was a little brutal last time. Oh well. Too bad. So I can't go to work for her defining an instrument that measures magnetic monopoles. Okay? So I've slammed the door on that career choice. If I have to adjust things if that's not true, but anyway. Now, this was so much fun. This math trick was so much fun that it begs that we pick out another math trick. And that is if I take the gradient of a scalar field phi, and then I take the curl of that, I'll always equal to 0. Okay. Now it's a little bit less obvious, but the Maxwell's equations that I want to play with on this one is the curl of E is equal to minus del B del T. Okay? Now if we were doing statics, circuit theory, the left-hand side would be 0, there'd be nothing that changes with time, and I'd have a del E equals 0, and I could see the relationship between E and the gradient of phi. Right? But a fact of life in this class is that everything is dynamic, that those time derivatives are wonderful. We want to keep those in there. And so we can't instantly apply that. But we can come pretty close. Because I can write B as the curl of A. Okay? So the right-hand side, I can write B as the curl of A. And I will interchange the order of differentiation. I could always do that, right? I could always choose to take the time derivative over the space first and the space derivative second. So I can always do that. And now I've got a curl on the left-hand side and a curl on the right-hand side. And so I can write my Maxwell's equation in a form that's closer to my trig identity. There's a joke there, but nobody can read my handwriting anyway, so it doesn't matter. And so this guy here is what will relate to the gradient of phi. And minus A is about the same as positive A. I'm sorry, minus 0 is about the same as negative 0, is positive 0. So I'll just slide in a minus sign there. It's not wrong, it's not right. It doesn't matter. 0 is equal to minus 0 is all I'm saying. And it's just a convention. Now, what was nice about this relationship here was if I know what A is, and I don't know what A is, but if I know what A is, then I take the derivative of A to get to B. Right? So this is the connection between the potentials and B. And notice, by the way, if I've futzed around with, if I've added a constant or something to A, I'll still get the same B. B is what kicks the electron around, so B is what the observable is. Okay? So the last thing I'm going to write today is I'm going to rearrange this a little bit. And I want to know what E is. And that's equal to minus the gradient of phi minus del A del T. And so this, if I cover this guy up here, this should be a very familiar formula to you. And it would be if there were no time variations. But with a moving magnetic field, I have an additional term that connects the electric scalar potential to the electric field. So again, if I have A and phi, simple derivatives get me down to E.